thanks, Mike, for making yourself available to give us this talk. And I guess we should also thank your hosts up on the volcano for all the good access they provided to you, and we all look forward to visiting the place. Just very briefly, by way of background, some of you have heard Mike speak before, but Mike obviously is a geologist. He was trained at Trinity College, Dublin. He's originally Dutch. So he finished he finished there, and he's still Dutch, of course, and he finished there in 1975. And like many young geologists from Europe at that time, he joined our South African Geological Survey in 1976, and he spent a couple of years there working for the Geological Survey. He then left, he saw the light, and he joined De Beers as an young exploration geologist, and ended up spending 29 years with the company, becoming one of the senior exploration managers. Like many of us, he then in turn left De Beers in 2008 and ended up in what we call the junior exploration and mining sector, and worked with a couple of companies, one of them being BRC in diamonds, and then Toledo, which worked extensively in Botswana. He now lives in Kleinmond down the road, so he's part of our very distinguished group of geologists in the Overberg. And thanks, Mike. We look forward to talking about the Salpeterkop Volcano, which interestingly is on our doorstep. And we all look forward to visiting it as well, to check out the work that you've done there. Thank you.
All right. Thanks very much, everybody, for giving me the opportunity to talk about Salpeterkop. My interest in Salpeterkop really started from a geomorphological point of view. It really is the best preserved volcano in South Africa. And provides an opportunity to look at some of the erosional history of this part of the world. But while looking at the geomorphology, I got very interested in the geology of the volcano. So I'm now in the process of building a geological map of this site, and so this work that I'm presenting is work in progress. It's spelled in various ways, but the Afrikaans spelling is normally the accepted one, Salpeterkop, but it's also known as Old Sneeuwkop in the older days. This is a photograph taken in July last year, and you can see it is one of the coldest places in South Africa, so for a visit it may be worthwhile doing that slightly before July. I just want to run through the location and some of the history, then go into the geology. I'm afraid I've got a lot of photographs of rocks, so I hope that is acceptable. Then talk a bit about the age, the geophysics, and of course some economics that people have looked at this site before, and come up with some sort of model of the intrusion. I'd like to thank Corlia and Andre at Roggeklof itself for their hospitality and their enthusiasm. Also, Uma Martinez has helped me a lot with the GIS. Sue Winkler and Marion Benford has looked at some of the fossil wood that we found there. Keith Kenyon helped me with some photography, and I've had some very interesting discussions with people who've been to the site and have worked on it from mainly a geochemical point of view. The site is about 350 kilometers north east of Hermanus, so it really is in easy distance for a weekend. It occurs just above the escarpment, which is shown here in blue. The site itself is very close to Sutherland. There's Sutherland on this Google Earth map. It's just off the main road before you get to Sutherland. The main estate is about 18,000 hectares, where they have some very nice game, including cheetahs. They've also bought a piece of ground just to the north of it, of about 3,500 hectares, on which Salpeterkop Volcano occurs. It is not connected at this stage. There's a road that runs between these two sites, but in the future, maybe this will become one estate. So that's where Roggeklof estate occurs. If you look at some of the 1901 map that was drawn up by Roger Jacob, that was drawn up by Casgrain, you can see that they refer to the site here at, on the farm at the time was called the Keep. It's now called Blauwboomwickies Keep. The site was called O Sneeuwkop or Salpeterkop in the English version. So it had a name of Old Sneeuwkop, and you saw the first photograph and the opening slide. It is quite a good reason for it. There's also quite a nice wine called Old Sneeuwkop that they sell at the Roggekloof estate. Just a bit of background on history. Sorry, I should go back to the previous slide. This site was visited by various people, including Robert Gordon from Gordon's Bay, if you like, who visited in late 1700s. There's a German, Liechtenstein, who wrote about the some of the rocks that occurred in the area, and also Andrew Wiley, who was the first Cape geologist, or the first geological surveyor of the Cape government of Cape Good Hope, and he arrived here in 1854 and visited the site in 1859. And he noted a few interesting things during his visit. He said he noted, and this is according to Rogers, who wrote about him, he noted that barytes were there, a mineral that people were interested in, and also that he would call this a feldspar trap. So he'd already recognized some of the minerals that occurred on this site. The first geological map that was produced of Salpeterkop was that of Rogers and de Toy in 1903. And it's quite amazing because de Toy only joined the Commission of Cape Good Hope in 1902. So he was fairly quick off the mark to map some of these areas in the Karoo, including Salpeterkop. And the next map that was produced was by De Wet, a MSc student from the University of Stellenbosch, who produced this map and looked at some of the rocks around this area, and really was the latest intensive mapping exercise that was done in the area. For Witt in 1990 wrote a bit about the structures around the volcano, and later with Luc Chevalier and Viljoen spoke a bit about the rare earths minerals associated with this occurrence, and recognized the presence of carbonatites. I'm busy now finalizing this geological map of the site, and it's almost completed, but I have to warn you that this is work in progress, so there's still a bit of work to complete to get this new map sorted out. In terms of its geological setting, this is a regional map of the geology. There's Salpeterkop in the middle. Sutherland would be just over here. And one thing to note is that it sits right at the edge of the southern occurrences of the Karoo dolerites. And it's intruded into what we call the Abraham's Kraal formation of the Beaufort sandstones, which is about 255 million years. So it intrudes into Beaufort sediments. It's part of a cluster of what we call, or a suite of what we call alkaline rocks in the area, and these are the main ones that I've mapped so far. I have to say that there are probably more around. The main ones are carbonatites in yellow. There are some kimberlites to the north. Whether they are related is another question. Then there are some potassium trachytes in white, some ultramafic, olivine melanotites, sorry, in green, and then some ultramafic rocks in purple. So the olivine melanotites are the ones that a lot of work have been done on it, particularly on the geochemistry. If you look at a satellite image, and this is there's a scale of 1 kilometer, the crater occurs in the center here with a peak to the north of it, which is not the crater, but it's actually the tephra, part of the tephra ring. But one thing to notice here, the circular circular strata of the Beaufort that surrounds this volcano, and that's really because of the updoming that occurred prior to the explosion. If you do a little flight plan, you will see that the main copy, if you like, is actually the part of the tephra ring, and the crater just occurs to the north of it. We're now flying west of the of Salpeterkop, and the Kop is right up here. It's 1,766 meters in elevation, and behind it is really where where the crater occurs. So this part of the elevated area is really the remnants of the crater rim and the breccias and pyroclastics that have been deposited just outside the crater. And in the distance, you can see the strata of the Beaufort curving round, which is a reflection of that updoming. Sorry, I shouldn't. This is just a quick one to refresh you. You see it's taken in July. There's still a bit of snow lying in the crater. There's the crater. There's a track going up to the parking area from here. It's a very nice climb up to the top, and you get a fabulous view of the area and also of the volcano itself. Okay, so I'm going to run through quickly about some main rock occurrences of Salpeterkop. There's Salpeterkop itself with the geological map draped over it, and we're looking and pointing into a northerly direction. And what I wanted to point out to you is you can see this up-down strata of the Beaufort dipping when you get close to the crater, dipping up to 40-50 degrees. So fairly steep dips, and then at about 5 kilometers away from the crater, the strata is almost horizontal. There are some of the updomed Beaufort sandstones. You can see the beautiful ripple marks on these sandstones, and again a ridge of these updomed sandstones with Salpeterkop at the background. The first that are here on this geological map are in orange. And that's really the fractured country rock, the fractured Beaufort sandstones. You can see how heavily this country rock is brecciated and fractured due to the pressure from prior the explosion. So they occur really on the outside up to probably 100 and 200 meters away from the crater. We then move into what I call the breccias, which are here in yellow. That you can see they're more rounded. They have moved quite substantially, but they predominantly are composed of the siltstones of your Beaufort, also occasionally dolerite glass. The matrix is highly altered. It's difficult often to see good textures, etc. Going into the pyroclastic breccias that occur just in the next to the crater, fairly coarse grained. They have got reworked almost like tufacitic materials. There are some tuffs embedded into it, but again mainly composed of lithic fragments, Beaufort fragments. There you can see them with some feldspars and volcanic clasts in the matrix. These rocks on this side of the volcano, on the northern side, are highly silicified, and that's really the reason why this is remnant that you saw from the aeroplane is stayed behind. It's extremely hard, and it's been silicified by later hydrothermal fluids that went through it. It also contains some interesting tuffs, but highly contorted due to the reworking and dumping of material that have been dumped on this tephra ring. And there are some veins that contain barite, which is a later event, and we'll get to that a bit later on. Then there are things that look much more bedded, and you can see there's some coarse bedding in these pyroclastics. I've tried to separate these from the unsorted breccias, and they certainly have dip and strike directions away from the crater. They are mainly, the tuffs that are interbedded are mainly composed of biotite and quartz, some goethite, and they do have isolated lapilli. These are some thin sections of those rocks, and you can see some of the lapilli that occur within them under the microscope. And then there is a sequence of pyroclastics that have a very shallow dip. These dips here from the bedded pyroclastics are fairly steep, but the reworked pyroclastic dips are very shallow, up to about 20 degrees. And you can see there the bedding is much more clear in these rocks. They also contain class of pyroclastic rocks that have been reworked. So I've interpreted these as reworked pyroclastics, probably reworking of a big pile of bedded pyroclastic that occurred on the northern side of the crater. And then outside the crater itself, there are what have been bedded, or that have been mapped by de Witt as trachytic pyroclastics. They're typical trachyte rocks. They contain some feldspar, porphyries, or phenocrysts in the matrix, but they are also quite nicely bedded. They were initially interpreted as ring dike explosions or ring separate explosions, but looking at them in detail, you can see the bedding in these rocks quite clearly, and there are some interesting dip and strike directions away from the crater. They also lie directly on bedrock. It may not be all that clear here, but those are these coarse trachytic pyroclastics lying directly on the shales and sandstones. Here's another example of a bedrock, and also the bedding within those units, and so on. So I've interpreted these as remnants of the ejecta that came out of the volcano, sitting on the side of the volcano. And if you look where they occur, and this is a photograph taken from the northwest, that's the tephra cone next to the volcano, and there is bedrock just underneath here, so the contact of that ejecta material is sitting quite close. Similarly, we see the contact down here, and you can easily sort of map out a paleosurface that existed, and that's now been partly eroded, but still that surface in part still being preserved on that area. There are some trachytes that have intruded into the country rock, and that's what they look like. They are mainly potassium feldspars with some minor nepheline and some biotite and apatites, and even some fluorite in them. But they occur mainly as dikes. The best exposure is well to the north of the volcano, and it's difficult to see any of those existing in what has been referred to as the trachyte pyroclastics. Now, going back into the crater, and after the explosion, we had a whole set of epiclastic sediments settling within the crater. They contain lapillistone beds, which are really the coarser units, and you can see how they cut across each other very nicely. There is a bit of a channel shape in there, but they're interbedded with some nicely bedded tuffs. And the tuffs have some, you can see there's some cross bedding in those tuffs that have been cut by the next set of beds. There are some ripple marks in those tuffs, very nicely preserved, but also some shales. So these are clearly water-lane sediments interbedded with your tuffs. And if you look in the thin section of those tuffs, they have some very nice gas escape structures. So some of these tuffs are still fairly hot when they when they were deposited. And the black is really the hematite that has replaced formed in some of these gas escape structures. That's a bit of a section through some of these epiclastic deposits, and you can see how steeply they are dipping into the crater. The crater is behind us. That's the edge of the southern edge of the volcano, and there's the carbonatite zone, the edge of the carbonatite zone, which is colored in red on this section. And then you go, there are some very coarse lapillistone volcaniclastics going into finer grained materials, and eventually into some shale, proper shales, water-laid shales. But note the dip of these beds into the crater, and we'll talk about that in a little bit later. Now the carbonatites that have come through appear to be much later. Well, not much later, but appear to be later. They occur in the form of thin diclets, fairly clean-looking carbonatite diclets, but also these are mainly the intrusive ones. Also occur as dikes and as sills. There's a big carbonatite sill right along the edge of the dome of the volcano, sitting there. That sill would be in there. So the carbonatite has really been is more pervasive and metasomatic rather than magmatic, in my view, and has replaced some of these epiclastic sediments. And there is a very nice example of these epiclastic sediments that have been completely carbonatized. And you can see these zones of carbonatite fluids that have gone through these rocks. So a fairly pervasive type of intrusion, and reflecting the presence of those carbonatites. That's looking over the crater to the south, and that's more or less the zone, and it has quite a sharp contact with the epiclastics, the unaltered epiclastics. So this is the zone where the carbonatite fluids have really replaced these epiclastics units, and that's looking in a southerly direction. I've turned this map around for that purpose. But we also have extrusive carbonatites, and this is just a little bit to the south of the volcano. There are various isolated outcrops of these carbonatites. There you can see a carbonatite dike coming through, and on the top there is a very coarse breath-shaded xenolith-rich carbonatite. And I'll show you the amount of xenoliths that occur in these rocks. And they weather out quite easily. These rocks have not been hydrothermally altered. And they weather out, and you get this pavement of these rounded xenoliths. These are mainly quartzites, hard, silicious quartzites that have weathered out of these carbonatites and form an amazing carpet of rounded quartzite bowls that have come out of these carbonatites. So the question is really, where have these quartzites come from? The vet did some work on that and suggested that they were Karoo related, because he didn't believe that these were part of the Cape Group sediments. But I think that these belong to the Cape Group sediments. They are very interesting around it. There are no percussion scars on these clasts, and they probably have been rounded in the volcanic process. But you can see that some of them are still bedded, and some of them are little conglomerates, and some of them have been phenatized by, I think, by the carbonatite fluids. Very interesting. But in addition to the mainly quartzite xenoliths, there are also things that look like the dwicatillite, also very well rounded, and some things that look like cyanide. So you get a mixture of these xenoliths that come out of these carbonatites.
Mike, can you just explain to the people what xenoliths are? There are a couple of people.
Okay, sorry, I apologize. Xenoliths are foreign material to the volcano that the volcano picks up as it goes to surface. So it tells you if you find certain rock xenoliths in these volcanics, it tells you a bit about where this volcanic rock has been and where it's picked up material from what is below us. So the main xenolith here is the quartzite, and it looks like those rocks are very similar to the rocks that you see around Hermanus. So it looks like those rocks extend right across into too close to Sutherland and have been picked up by the volcanoes as it came from greater depth. I'll just show you a photomicrograph of these quartzites, and it clearly shows that they are not Karoo sandstones. They have got granoblastic textures, they've got quartz overgrowth, and are clearly part of the Cape group sediments. This is just a micrograph to show you the tillites, the Dwight tillites that have been picked up by the volcano. So quite an interesting stratigraphy that we can start unraveling from what it's come through. And finally, some photomicrographs of the what I think are altered cyanides. You can see the nephilines in it. There are some natrite crystals. There are some lots of feldspar. But one thing that is notable is how altered it is and how carbonatized it is. So it really is taken a hammering by the later carbonatite phase that came through it. So this may represents a volcanic chamber that existed below the volcano and tells us a bit about it. There are some younger volcanic vents on the side of the volcano, and they've got also some interesting class in it. They are not altered at all, not like the main pyroclastic and breccias. These are unaltered rocks. They contain, interesting enough, also some Dwight class, but also some carbonatite class. And this particularly vent is actually cut through a carbonatite set of dikes. So that gives you a bit of an idea on the age relationships. There's some lithic tuffs that occur in these volcanic, younger volcanic units that are also mainly composed of alkaline feldspar. And then on the northwestern side, there's a very interesting suite of pyroclastics or volcaniclastic sediments that are very steeply dipping to the north. I have not worked out what the meaning of this is yet. It came quite late in my mapping that I found these outcrops. It's got interesting polished class that suggests maybe that they've picked up some of the Dwight. But you can see the bedding in these pyroclastics. It goes on for about 300 meters, and also contains some fossil wood and some granulites that have probably come from the Natal Metamorphic Belt, also below us in the Salpeterkop. The final phase really is the hydrothermal alteration, and these are some of the pyroclastics, and you can see how this has been hydrothermally altered by silicification, incredible intense solidification that is pervasive to these rocks, and haven't really got as far as the center of this particular boulder. But it is a great example, and if you look very carefully at the silicified area, they're identical to the unsilicified part of it, but it highlights the hydrothermal alteration, which is most likely associated with the later carbonatites. In addition to that, this is looking north now from within the crater to that Salpeterkop itself. There are some interesting black and dark brown streaks along here, which very much look like the later femoral activity. The black is mainly manganese, the iron is mainly red, and you get these iron and red oxides that have been brought up by later gas activity at the end of the life of the volcano. And this part is highly ferruginized, if you like, during that process. And it really also is shown in those that gas activity that I showed you early on in the tuffs itself. There's some more of this fumarole activity, this later gas activity. These are quite strong gas lines cutting through the breccias. They're they contain phlogopite, so some of them may still have had some fluids with it. This is one of the holes that was dug by the early guys and looking at these volcanoes, and it's unclear what they were looking for, but I think they were mainly after barite at the time. But again, you can see the gas streaming here, and just to put you in the picture, that hole, those holes occurs at the bottom of that pyroclastic pile. Just below here, you would get the bedrock, the brecciated bedrock of the Abraham's Kraals formation. Now, if you go inside these tunnels, this is only about 20 meters deep. The ceiling is made of proper saltpeter, and this is really where the name, I guess, saltpeter comes from. It's salts that have been leaked by meteoric water through the rocks and deposited in almost like stalactite type salt. It's very soft. And I took a sample of that. It's mainly composed of manganese, actually. So this would then be a nitro magnetite produced by these very much later meteoric rocks, meteoric waters. Okay, let's just go back to that section that we drew. It's dipping quite steeply into the caldera, and there's some interesting traverse ridges, which I think represents gravity flow and of rocks on the steep bedding, and also you'll see some slip structures in there. So these rocks were later they were deposited in the fairly flat conditions at the bottom of the crater lake, but the crater lake then must have collapsed to some extent to dip these beds quite steeply into the center of the crater. And I think this is part of the crater collapse that occurred after the last carbonatite phase of this intrusion. Now, if we look at the age of this carbonatite, this is another photograph of some of these pyroclastics, and you can see there's some dolerite in there. And these are very similar to the Karoo dolerites. So it's at least post-Karoo, and that's what we know already, because, or at least post-dolerite Karoo, so it's post 180 million years. Some of the dating that has been done, particularly here near Sutherland, with work that Farners Fillion has done and so on. The ages coming between, the initial ages were about 74, a later age produced an age of 66. There are some older ages here of these olivine melanotites north of Salpeterkop and both west of Salpeterkop, which comes to the same sort of age. So we're looking at a sort of late Cretaceous intrusion. And interesting enough, there is a kimberlite that was dated. It's not a good date, so it's unclear what that means, and it's also unclear whether these are really related to this alkaline complex. In addition to the dating, and I'm presently looking for some samples to see if we can get some dating done on the actual crater, which we don't have. As I mentioned, the dates are only related to the, they're only done on the olivine melanotites. So we don't really know when the crater was in place, probably not much dissimilar in age, but there's some fossil wood that we found inside the crater associated with those epiclastic sediments. There's the position of that fossil wood, and you can see the tree lines in this wood. It's quite well preserved, and Marion Benford of the University of Witwatersrand was able to identify this as a Kochpresoniloxone, It's a late Cretaceous, early Tertiary wood that is related to the Clanwilliam cedar population. It's a conifer, but the study of the cell structures of the wood, which is very well preserved, and one can study that in great detail by taking thin sections of this wood, suggests that it was that the climate at the time was one that was fairly stable, and because it doesn't show major changes in the growth ring, and it suggests that the climate was warm and humid, quite different than what it is now, with little or no seasonality, and it supports a sort of global record of a warm late Cretaceous period. So it's been very useful to get an idea of what the paleo environment was like at the time of the intrusion. I found quite a lot more fossil wood. Unfortunately, it's not very well preserved, so at this stage we can't really use it, but I'm sure that we'll find more, so we can try and expand on the paleo environmental interpretation. Okay, so I just wanted to show you some satellite images using some free available spectral analysis of, first of all, the European satellite. And this shows you very interestingly, this is a false color image, but it shows you in red is the iron window, and it shows quite clearly how rich this area is in iron, except for the Salpeterkop itself, which is highly silicified, and shows you very different signatures. So it can sort of highlight different things that you may use in your mapping program. There's the crater, more or less, and it shows quite clearly how there is an outlet here and a fan of material that came out of the volcano, clearly having the same sort of iron-rich composition. There's another satellite called the Aster, which is also free. One can use it, and this is all work done by Uma Martinez, who helped me with this. But I wanted to show you this one here. It shows you the silicate ratios in white. Sorry, it's in white is very high. It's a silica. It's iron over silica ratio, and in white is the high iron ratios, and in dark is the high silica ratio. And again, it highlights very clearly the silicification and the hydrothermal alteration of these rocks. Again, shown in this one where the dark color is high silica content compared to the rest of the area. So very useful technology that can use in your mapping of these rocks. This is a bit of a regional photograph, also an Aster image. There's Salpeterkop itself, but this particularly ratio of colors enhances the structure quite clearly, and you can see there are some major structures here, northeast southwest structures coming through, and also a very strong structural trend coming through from east to west. That's the escarpment, and those are, again, I must emphasize that these are false colors, so it's mixing colors to try and enhance certain features. And it's the work done by Newton in '87 and has already highlighted this very strong northeast southwest structure, as well as this east-west structure. So the Salpeterkop volcano lies on major structure intersections, and it obviously followed a weakness in the crustal areas. Some work that the Council of Geoscience have done, or Geological Survey in 1993 by Edgar Stettler and company. They did some gravity work over the volcano and produced a very strong gravity low, which suggested a low density rocks underneath. And they came up with an area of about 7 by 4 kilometers at 3 kilometers depth, which is more or less at the contact of the Karoo Capes rocks with the Namaqua-Momwell belt, so the middle upper crust and the middle crust. They also suggested that based on the gravity that the central vent or the breccia vent is about 400 meters deep. So it gives one some idea of what this thing looks like in 3 dimensions and more at depth. In addition to the gravity, they also flew a radiometric survey. It was a time when people, this survey was flown already in the 60s when the uranium boom hit the Karoo and a lot of areas were flown radiometrically. This is a reinterpretation by Edgar. A strong thorium and some uranium content associated with this rock. With these rocks, so it certainly highlights the importance of certainly the feldspars and so on. Okay, just a bit of background on the exploration history of time. In the 80s, when diamonds were found in Kimberley, people were looking at certainly Silver Dam, which is an ultra basic rock, and has similarities to kimberlite if you look at enhanced specimens. And there are some holes here and there that people dug, that they were looking for diamonds. But that lapsed pretty quickly. During the uranium boom in the 70s, Rand Mines flew a regional radiometric survey, which I showed you parts of just now. Their interest was really niobium, zirconium, titanium, but also rare earth elements and zinc. Barium at the time and fluoride were for them for second interest. They did a lot of drilling on the crater, and you can still see some of the drill holes that are left behind, and I've got some cores still that I managed to relocate. So there's a lot of information still available on that. And the geochemical interesting anomalies were mainly associated with the carbonatite breccias and their hydrothermal alteration products. They did some bulk testing, and that really showed, this was in the 70s, that metallurgically it would have been a big challenge. So they walked away. They, however, did look at some of the samples for gold and found some gold anomalies. They did some more sampling, found some more gold, then did a joint venture with Rio Tinto, who resampled the area and really didn't find anything of interest. So that's really the amount of work that was done from an economic point of view. And you can see I've plotted some of these boreholes that I've found, and there are quite a number of logs still available. So with that, I hope this is a line of boreholes here from 49 to 44, for instance. This is a brecciated country rock, and there you can see the invasive areas of the carbonatites that have come into these breccias. But it's going to be useful to try and build a 3D model of this volcano using some of those logs. This is an example of their, this is our niobium results, mainly associated north is to the side of the slide, mainly associated with the carbonatites. And then perhaps show you a couple of pictures of some of the interesting minerals. These are the barytes that occur in some of the breccias. There's some beautiful natrolite crystals that have grown quite close to the contact of the carbonatite zone and the epiclastics. Just a bit of background on the thickness of the Karoo in this part of the world. There's Salpeterkop, there's Sutherland. These are holes that were drilled by Sucor in the 60s when they were looking for oil in the Karoo. But it shows you, for instance, these holes, this hole here has about 2,000 meters of Karoo sediments before they go into TMS, into the Cape sediments that we see here on the coast at Hermanus, for instance. Interesting here, though, is they didn't intersect any Wittenberg group sediments, so these thin out towards Sutherland. On the other side of the Salpeterkop here, the Cape sediments have been are not present, and you go straight into the Namaqua Natal Mobile Belt granulites and basement rocks. So somewhere along this line here is the end of the Cape Group sediments. And projecting these various boreholes, it's estimated that we have about 2.5 kilometers of Karoo rocks sitting underneath Salpeterkop. Some seismic work that was done not far from here, there's a north-south section, about 70 kilometers to the east of Salpeterkop, highlights this as well. It shows the Karoo rocks at about 2 kilometers, 2.5 kilometers. And then below that, this sort of darker area here are the Cape rocks before you go into the Namaqua Mobile Belt, which is referred to as the middle crust and the lower crust. And then the moho, the contact between the crust and the mantle, sitting at about 42 kilometers depth. So this line here is more or less projected line of where Salpeterkop sit, and it cuts, for those who are interested in it, cuts to part of the BT magnetic anomaly that sits in the middle crust. Just interesting stuff that we still have to sort of look at. In terms of a model, this is a slide from a paper by Phil Jenny, who looked at various olivine melanotites associated with Salpeterkop and further south. And you can see the ages. There's an age progression from south to north. And he feels that although there is this is associated with the movement of the African plate, that you probably had bob-like upwellings or melt migration at the base of the lithosphere, which is in the order of 150 kilometers, or perhaps along weak lithophilic zones that brought up these various magmas. There's another idea by Hamrichhausen, who suggested that you had two types of plumes that generated this age progression, and he certainly highlighted that offshore, where he can follow some of these alkaline lineaments, magmatic lineaments, both north of us and also the one associated with Salpeterkop. So there are various ideas on the development of Salpeterkop, but that is still something that people will talk about. I just want to take you now to finish off with some cartoon diagrams, which I'm probably now touching on things that are perhaps just outside my knowledge completely, but I want to give it a try. And it looks like at late Cretaceous times, you had a heating, what we call, of or partial melting of the mantle below Sutherland, and that could well have been associated with what we call the African superplume. The African superplume is highly regarded as causing the major uplift of southern Africa, and that heat would have come from the core mantle boundary. Heating would have resulted in melting at the base of the lithosphere at about, say, between 150 to 200 kilometers. And your carbonate-rich smells, your primary magma, would then form your first olivine melanotites and ultramafic lamphorites, which would then have intruded to the surface. So those were the first ones to come up. A melting of the lithosphere induced by deeper source carbonatite melts produced more silicate magmas, and this is when I think you've had a major input of cyanide starting to develop at about 2-3 kilometers depth, which is what the geophysics tells us, and that's sitting at the edge of the Namaqua basement and the Cape and Dwika sediments. You had massive volatiles coming through with mainly H2O and CO2, causing updoming and holding back the explosion by the overburden magma, of the overburden sediments, and then a massive explosion of trachyte, which is a feldspar-rich rock that produced the main deposits around the volcano. So you've had a nice tephra cone, which we still have part of preserved. You've got ejecta material on the side of the edge of the dome, but also things coming up with dolerites that have been cut through, and other mainly Karoo sedimentary rocks here. So some of the alkaline carbonatite fluids would have phenatized the country rock. As I say, this would have been a very large explosion, a one-off probably, that produced the volcano. Then the carbonatites evolved from the primitive liquids by a low degree of melting of perhaps carbonatized and alpha-peritites. The carbonatites would have followed the same conduits as the earlier volcanic vents, and they would have been more passive in their intrusion, lots of dikes and sills, with some side flows and producing some odd carbonatite breccias, but also bringing up substantial number of these Cape xenoliths from the Cape supergroup, xenoliths from the original magma chamber, and also from the Dwika. This would have caused the crater collapse to some extent, and resulted in the steeply dipping beds into the crater. The crater would have been filled with water, trees started to grow, and we would have had some later events bringing up the finals of volcanic activity of this volcano. The question really still is of how quickly and when did that carbonatite come through. Now, I have found one or two sites where carbonatite dikes have been cut by olivine melalotite dikes. So I get the feeling that this whole these stages 1 to 5 happened quite quickly, actually. It is with carbonatites mainly coming to the end, but there may have been some precursor carbonatite intrusions here right in the beginning. So I think that's really where we are today. We have remnants of these pyroclastics sitting on the side. We've got a remnant cone sitting. We've got a crater with fossil wood in it. So it really tells us that there is, since the intrusion, the emplacement of this volcano, there has been very little erosion in this area. So we see from the late Cretaceous onwards that erosion was limited. And we know that further north there is a volcano called Stompor. It's about 70 odd million years. It contains a crater with fossils, lots of fossil fish and frogs, also beautifully preserved. And we also know from the offshore records that we had a major change in erosion at the end of the Cretaceous. So at the end of, say, 65 million years, things changed quite rapidly, and we can see that in the climatic cooling that went right into the Cainozoic. So that's as far as I can take it. It's work in progress. I still have to try and find some minerals for more accurate dating, which I'm busy with. But it's a site not far from Hermanus, 350 kilometers. It's a great weekend or two-night overstay. There's great accommodation at Roggeklof. They can house quite big groups. They are well equipped to house groups. They have some nice, good wines. They're great. Some very nice wildlife, many cheetahs that are in their game reserve, and it's also great for star viewing. So it may be a great visit to make with a group from Hermanus if people are interested. Thank you very much.
Thanks, Michael. Okay, lots to discuss, and I'm sure there are lots of questions. If I can just kick off to get the discussion going, and it's almost an aside, but that barytes that was being looked for, Mike, I mean, you might have done some work, but and we've got, I think, some medics on the talk, but barytes is very interesting from a medical point of view. It blocks X-rays, and I think most of us will know it also works very well as a barium enema if they want to look at your innards. So, you know, and the old medics used it quite extensively way back then. They used it as for building the housings of the early X-ray systems. Obviously, today it's worked extensively or used extensively in drill muds, which it stops blowouts. It's very heavy, but that's just a bit of an aside. So. Interesting that they found barytes back in the volcano in the early years. Right, question time.
Mark, can I start it off, please, John?
Sure, go for it.
Mike, those very, very fine, bright yellow veins that we saw in that one hydrothermal outcrop slide that you showed, are those by any chance secondary uranium minerals, something like conatite or uranophane?
Keith, I don't know, actually. I have to say that my focus was really to look at the geology. I haven't really done a hell of a lot of geochemistry on it. I'm not a geochemist, and a lot of people have done geochemistry on various parts, so I thought I'd try and leave that out a bit. And as I mentioned, my interest is really to link this in with the geomorphological and erosion history of this part of the world, which I'm trying to work on and use this as a benchmark. But yeah, it's something certainly that that could be looked at. And I think in terms of, one must remember that from an economic side, this was looked at in the 70s and 80s. Things have moved on tremendously, and particularly with regard to the rare earths. So, you know, Keith, it'll be interesting to look at those from that point of view.
I'd just like to add one more point. Those gold values that you showed, those are done by Rand Mines and various South African gold mining companies. Any low-grade gold deposit assayed before mid-90s by any South African mining company, whether it be Anglo-American or whatever, is hugely contaminated because they use their mine labs, which if you put a blank in them, would analyze at around about 30 grams a ton. So quite a lot of those older gold assays should be treated with a pinch of salt.
Well, you're quite right. I mean, that's what Rio Tinto, they put quite a bit of money into it to resample the area and found very little. The gold analysis done by Rand Mines was all done in the 80s. So, and they produced some amazing targets. And I looked at these things and there's nothing. So yeah, I think you're quite right. So a lot of these would have been contaminated.
Well, let's get Adrian's comment on that as well.
Yeah.
Ex-Rand Mines. So.
Absolutely confirm that. Because the company was run by mining engineers, they thought it's operation and have the gold assayed at the ERPM laboratory and assay lab. And after a while, we were getting spurious results, not just Salpeterkop, all over what was then the Northern Transvaal, the LTCL lands thing. And eventually, with a bit of new management, we said, well, you know, we mustn't do this. There's no point in saving a couple of rand a sample and chasing geologists all over the country looking for spurious gold deposits. So, yeah, that certainly was an issue. Be interesting to look at the metallurgy and you know, what was the state of niobium extraction back then compared to now. Is that kind of information available, Mike?
Yeah, I do have some of these metallurgical reports actually. Thanks for some of the guys that I spoke to, gave me quite a lot of the old material, also some of the drill logs and so on. So yes, I could try and get it to you and you have a look at it, see what you think.
Yeah, I'll have to ask somebody else to look at it, but it'd be interesting to know what you did.
It was mainly done by Mintech actually.
Ah, that could be good or bad. It was done some time ago, so it might have been good.
Yeah.
Okay. And Mike, just to go back to a comment about the timing, I mean, it's amazing how quickly these volcanic edifices or volcanoes grow. And just for interest, and I'm doing a bit of a sales talk here, I'm going to talk about Mount St. Helens next week. And, you know, Mount St. Helens blew its top in May 1980. And a lot of the deposits that you found, obviously it's a different composition volcano, but it's, you know, it's fascinating if you go and look at the modern context like St. Helens and talk about the rocks you've talked about today, just to see how quickly these events happen. So for those of you who might be interested, particularly our non-geological audience, I have a very spectacular set of photographs of the whole volcanic process or the eruption happening. And it'd be very interesting for you to watch that and then, you know, go back and better understand some of these features that Mike talked about today.
I
wanted to ask
yes,
more
here's a
about
question. Here is a question.
We'll come back to you, Bastien.
Oh, yes, it's his question.
Okay.
Do you think the volcanoes erupted more in a tropical forest landscape or in a dry and empty Karoo? Is that what you want to ask, Bastien?
Yes, I wanted a little bit more detail about the mention of the wood fossils and the paleo environment where this sort of volcano exploded, because I think there are not many examples in Southern Africa, and I imagine they erupt in the middle of the continents. And my understanding is that the wood indicate that it's a little bit of water, but I wanted Mike to comment if he has an idea of what was the landscape when the kimberlites and this volcano exploded, if it was mostly arid like today in the Karoo, or if it was like maybe like in the Congo where there is a huge forest. That was my question for Mike, if we have time.
Okay. Well, as I mentioned, I found quite a bit of wood actually, and unfortunately, Marion was only able to identify one section, but we'll have to work on that a bit. There's definitely potential for finding more wood. So I want to take Marion up there one day because, you know, she may be able to pick up things that a geologist like myself may miss. But it clearly looks that there was water around. There are some nice shales at the top of the crater. The wood itself suggests that the climate was fairly steady and warm and humid. Whether it was a forest, tropical forest, is difficult to say at this stage. But you must remember there are some other volcanoes like this, like Stompor, and we'll have to just go back to those things to try see if we can get better handle on the paleo environments of these of this time of of the geological history, because it is an important period with the end of the sort of major phases of erosion and the changes in climates and so on. So it's an interesting one to follow up on.
So, Mike, you're saying it's not necessarily fossilized xenoliths, it's actually wood that was incorporated during the eruption.
It was wood, no, it was wood that grew as trees after the eruption, and you had the crater forming, and the crater had water, and then trees would grow around it, and fall into the lake and get buried by subsequent collapse of sidewalls and so on. And then the water gets silicified, or the wood gets silicified and preserved. And as you could see from those two thin sections, you can actually, the preservation is almost molecular changes of silica, replacing it on a molecular basis. So you're preserving the cell structures almost intact, so you can tell a lot about what species you're looking at. And unfortunately, we don't have a lot of that type of wood from that period in South Africa. But we'll work on it. It's work in progress.
I wanted to comment that I've visited some very recent volcanoes and sort of intrusive rock in America, in the desert, and it's very it's mostly dry. It's only in small canyon where they have a little bit of wood. And you mentioned that some wood were maybe only in the volcanoes and that there is few fossils of frogs. But I wanted to know if you imagine the environment more like a Colorado plateau where it's mostly dry everywhere, or if it was if there was a lot going on around rivers and a lot of activities. But yeah, thanks for your answer, Mike. I'll be keen to visit one day.
Yeah, I'll bring you come up and we'll have a look around. Bring your drone.
Okay. Well, Mike, I mean, just one of the suggestions, and we've talked about it briefly, is that one of these days we have a visit to the volcano, you know, with people who are interested, geologists and non-geologists. Obviously, you know, Hermanus people would be most welcome, and we go and I think that's your intent, that there will be sort of a walk around tour or a guided tour across the volcano, and you can actually, you know, see these features firsthand.
That's a very good idea.
Yeah, and just to go back to a lot of those breccias and features you show, Mike, I mean, there was obviously, you know, magma-water interaction or phreatomagmatism, you know, helping to drive the process. You know, some of those clasts you showed are quite angular, and I imagine even the rounding, you know, would be part of a very active volcanic process going on in the throat of the volcano, with or through interaction with water, you know, much like you see in Mount St. Helens.
Yeah, I think the phreatomagmatism must have happened, must have occurred as well, and particular. You know, at that time of the Cretaceous would have been a lot of water around. There would have been some water around, so yeah. The Karoo would have had the Karoo
groundwater,
some reasonable water tables.
Yeah. Okay. Anyone else?
John, I just wanted to talk to Mike, hear what Mike has to say about the erosional history. You know, given the intrusion date of this, let's say 75 million or whatever it is, and Kimberley sitting at 90 million, you see this Salpeterkop intruding into the Beaufort. There's, Mike, I presume, no evidence of any other rocks like basalt or anything like that. So between the time of the Kimberley intrusion and, you know, given that, you know, lots of workers have said there's maybe 1.5 kilometers of erosion around Kimberley, it kind of brackets, doesn't it, Mike, the, you know, an intense period of erosion between that million and 70 million. And I wondered if you had any ideas on, maybe thoughts on, you know, how far the Karoo basalts extended across you know, southern Africa at one time, and how much stripping is actually taking place, because it does seem that the western side, you know, was more actively eroded than, say, the eastern side of southern Africa around that time.
Bill, that's really my interest in this project initially, to get some ideas on this erosional history. There are no basalts class at all. There's nothing that looks like Upper Karoo in here that I've seen, but again, a lot of the material is fairly altered. But it looks like it's maybe Beaufort sediments, some Dryka, and the cape underneath it. Whether the basalts came as far as here, we have to assume it must have, but it may have been a lot thinner. And we may not have had the great thicknesses of the Upper Karoo in this part of the world. We'd have to, you know, there are some kimberlites there that appear to be older, so I haven't really looked at those, and that may be a good starting point to go back to and see if there's anything that one can learn from those.
Yeah. Anyone else? Thanks everyone for the great turnout, and thanks Mike for the presentation. Thanks, Letitia, for your contribution from your group, and it's good to see that both groups were working really well. And thanks, Henny, for your efficient management. Worked like a bomb today.